So today we're moving on to Chapter 6, starting with 6.1, which is basically it's area problems. Now, you guys have already been introduced to to integrals representing areas. We know that one of the first things you learned about the integral is that if this is y equals f of x, and these are 2 points in the domain, a to b, then this green area right here is the integral from a to b of f of x dx. So today, what we're going to be doing is taking this concept and kind of running with it. Let's see what other types of shapes can we find the area of. Finding the area of shapes is actually a very old problem that goes way back to some of the founding societies involved in mathematics, such as the Greeks. So the Greeks were very concerned with finding areas of common shapes as well as volumes, and they were able to develop formulas for areas of triangles, rectangles, parallelograms, rhombuses, polygons of all different types and shapes, like pentagons, hexagons, cones, cylinders. One of the hardest ones, you know what? The hardest shape of all was actually one of the most simple, is the circle. You guys know why the Greeks had such a big problem trying to find the area of a circle? It's because they didn't really know what pi was. In fact, for a while, a few thousand years ago, maybe about 2,000 years ago, some people thought that pi was equal to 22 over 7. You should try this on your calculator. Plug in 22 over 7, and you get, like, the first 3 digits are actually right. And then eventually it's not quite equal to pi, but there was a time when they thought that this was pi. Pretty interesting. And in order to figure out the area of shapes like circles, they would try these various tricks, like see if you could enclose it in a polygon with a whole bunch of sides. And you might notice that the more sides you include on this polygon, the closer you're going to get to an actual circle. All right, if I add another side here, and another side here, and another side here, and so forth. So that was the sort of stuff that they had to resort to in order to calculate some of these pretty basic and essential areas. The things that you learned, you definitely learned them in geometry in high school. You probably learned them in middle school even. Like, it's really fundamental stuff. Well, for all those plane geometry shapes that you learned areas for back in high school geometry, most of those formulas you were probably just given. And one of the amazing things that came out of calculus was a whole new way to calculate the areas of all these shapes and a whole bunch more. So you will find that we can actually rederive almost any area formula you've ever learned can now be rederived, often in a pretty simple way, surprisingly simple way, using calculus. So for example, I could show you how to come up with a formula for the area of a circle. I'm not going to do that one today because it uses a technique of integration known as trig substitution, which I haven't taught you guys yet. Although, strangely enough, it's actually easier to come up with a formula for the volume of a sphere. So I'm going to show you that probably on Wednesday, a really easy way. Like, it takes like 2 minutes, and poof, you've got the volume of a sphere formula, which eluded the Greeks for, hundreds of years, if not thousands. And then everything was made possible when Newton came along with his calculus. So let's go back to this very basic picture I saw, and look at this green shape right here. It has a graph on top, y equals f of x. The two sides are two numbers a and b, and the bottom is the x-axis. So now let's try and take this one step farther. Let's add in another function. How about this guy, y equals g of x? And what I want to find is not the area below everything, but the area between f and g. Can we get an expression for that based on what we've already learned? We can, if you notice that you can get the blue area by taking the green area and then subtracting off, well, I didn't assign a color to it yet. Does that make sense when I start describing shapes on the board by their colors? Yeah. Okay. So you can't. So you take the green area, subtract off the orange area, and you get the blue area, which leads us to the following formula. If f of x is bigger than equal than g of x on some interval a, b, the area between, and what I should really say is below, but the area between f and g on AB is, well, according to the picture that I just saw, it'll be the integral from a to b of f of x dx, and then subtract off the integral from a to b of g of x dx. And I might as well just combine this into a single integral as the integral from a to b of f of x minus g of x dx. So let's do an example. Let's make this function y equals x squared. Let's make this function y equals 10 minus x squared. Let's say and this is 1, 2, 3, 4. I want to find this area. So we can just use the formula that I just gave you. You simply need to identify what is f and g and the limits of integration. F is the function on top. Notice it's kind of important that you are able to identify which function is on top. So it's kind of obvious when you can look at the picture. It'll be a bit less obvious when you do your homework and you have to come up with this picture yourself. So that'll be lots of practice with graphing functions. All that stuff that you had to do in pre-calculus is now very important. What's the function on top? In other words, my f in this picture. The 10 minus x squared. And the function on the bottom is just the x squared. And my two limits from 0 to 2. Thus, we get the integral from 0 to 2 of 10 minus x squared minus, well, x squared. So that's the integral from 0 to 2 of 10 minus 2x squared, which is equal to 10x minus 2x cubed over 3. from 0 to 2, which is equal to 10 times 2 minus 2 times 2 cubed over 3. That's equal to 20. What is that? 816 over 3. So I could write that as 14 and 2/3. Okay, not so bad. That does it for this, but now let me alter the example a little bit, because a lot of the time a question is not going to be as clear-cut as this. It was kind of nice in that I told you, at least I clearly illustrated in the picture, what the two limits were. But more typically, a question might say, just find the area between two curves. So forget about 0 and 2. Those were kind of artificial. Now I just want the area between this curve and this one, the area that's trapped between the two of them. So the only difference in this new example is that I'm not specifying the two endpoints, A and B, anymore. And what I'm asking for is all the area that's trapped between the two of them. So this kind of weird greenish shape that looks like, I don't know what the heck that is, but it's this big green blob here. Is if we want to apply what we've already learned, can we? Yes? Okay, that is exactly what we're going to have to do, because since I didn't give you what the two endpoints were, you can see that one endpoint is where the graphs intersect here. The other endpoint is where the graphs intersect on the right. So let's find these 2 points right here. By doing what was your name? Elvin? Huh. Like Elvin Jones, man. He's a badass jazz drummer. So let's do what Elvin suggested and find the intersection of those two curves by setting them equal to each other. So set x squared equal to 10 minus x squared. So 2x squared is equal to 10. X squared is equal to 5. And x is plus or minus root 5. So my this point right here is positive root 5, and this point right here is negative root 5. Then the green area is, well, we have our A and B now. They're plus and minus root 5, and we get negative root 5 to root 5 of 10 minus x squared minus x squared. And I think you guys could compute that. Yeah, I don't need to bother computing that. Any questions?
Mm-hmm. 10, why aren't you subtracting f of x from d of x? Or from, sorry, f of x from g of x instead of the other way around?
Yeah, how do you know which one to subtract from which? So the way we started off the first example, the first thing we had to figure out here was which one was f and which one was g. How did we know? It was nice because we had the picture. And in the picture, what you needed to figure out was which is the one on top. And the one on top was the 10 minus x squared. The one on the bottom was the x squared. So you subtract the one on the bottom from the one on the top. But sometimes it's not always that obvious. Like, what would have happened if I hadn't realized this? And what if I had done x squared minus 10 minus x squared instead? What if I had done this integral? Then what would have happened? Can we say what answer I would have gotten? It would be the negative, yeah, of the other answer. It would be the negative of this answer, or of this answer in the first example. So since I'm asking about area, one thing is that area can't be negative. Right? Strictly speaking, it doesn't make sense to have a negative area. And if I'm asking you for an area, it's assumed I mean a positive area. Now, all that said, I have introduced the concept of a signed area in this class. So if you did this and got a negative answer, that would be a hint that you chose the wrong function on top and the wrong one on bottom. It's also possible that you might have something like this. Here's f, and here's g, and if here's a, and here's b, then when I integrate f minus g, I'll get, let's see if I can draw this. I'll get some positive area here, and I'll get some negative area here. Oops. I'll get negative area here, and they'll cancel each other out to some extent. So just like when we first were introduced to integrals as area, and you found out that area below the x-axis counts as negative area, the same thing still holds. In fact, it's probably worth pointing out that the area between f and g, i.e. the integral of f minus g, you could also think of that it's equivalently the area under y equals f minus g. So that's another way to think about this, is i.e. the signed area between f minus g and the y-axis, or sorry, the x-axis. So that's a totally equivalent way of thinking about these area problems. You could think of it as the area between two graphs, or you could think of it as the area underneath this, but above the x-axis.
What do you mean by signed? Like positive and negative?
Yeah, that's, so yeah, when I say signed area, that means we're also allowing area to be negative, which is the case when it's below the x-axis. Like in this example, if I integrated f minus g, I'd get some negative area. So in fact, just by looking at this picture roughly, would you expect a positive or negative answer for the integral of f minus g here from a to b? It looks like there's a little bit more negative area than positive area. So yeah, I would probably, just based on this picture roughly, it looks like we would get a negative answer for this guy. Let's do another example. This time, I am going to look at the function y equals square root of x. And this example is going to introduce another technique that you can use in evaluating these. We can get this area that I'm asking for pretty easily using what we already know. It's going to be the integral from 0 to 9 of square root x dx. So that is the integral from 0 to 9 of x to the 1/2 dx, which is x to the 3/2 times 2/3 from 0 to 9. That's 2/3 times 9 to the 3/2. That is 2/3 times 27, which is 18. Not so bad. But I'm going to show you another way we could do that, which, even though this problem wasn't so bad, the technique that I'm about to show you will be very useful on some harder problems. See, this square root is kind of annoying. It's kind of a pain to have to integrate sometimes. So in fact, okay, let me redraw this picture on its side. I'm going to turn this picture sideways. I'm going to interchange the x and y axes. In fact, let me say by drawing it on its side. Like this. If y was equal to the square root of x, what's the formula for it when I draw it on its side? Because from this guy, this is the same as x equals y squared. So if I just interchange the two axes, this is the same as y equals x squared, as we're all very familiar with, because it's like the most common example used in all of calculus is y equals x squared. So I can also do this problem by calculating the area this way. And in fact, now we can use our new formula by what we need to determine what the function on top is and what the limits are. So can you guys see that this line right here is the function on top? And what's the equation of this line? Y equals 9. Or how about, yeah, I'll just say y equals 9 is on top. Y equals x squared is on bottom. And if you plug in, you can see what the x-coordinate that goes along with this point is. It's obviously 3. So a is 0 and b is 3. And we get the integral from 0 to 3 of 9 minus x squared dx. Do we know what the answer is, or what we expect? 18, yeah, we better get 18. I'm going to know I messed up if I don't get 18 here. I get 9x minus x cubed over 3 from 0 to 3. So I get 9 times 3 minus 3 cubed over 3, which is 27 minus 27 over 3, which is 27 minus 9, which is 18. Okay, good. So everything's consistent so far. What I want to show you now is a third way to do it where we don't have to redraw it on its side. So the alternate way that I could have done the steps in order to calculate this integral, and maybe you guys haven't seen this before, is to make this a y integral instead of an x integral. You guys done that before? So I can integrate with respect to y as well. So alternately, let's just go back to this one. Here's 9. Here's y equals root x. Instead of 0 to 9, the integral of root x dx, we're going to change the integral of the variable of integration and make it with respect to y instead. And what you're going to notice is it's all going to look super familiar because it's exactly what I did here. The only difference is I'm calling what I was calling x here, I'm going to call y here. And I'm not going to bother redrawing it on its side. But other than that, it's the exact same calculation. So now we're going to integrate from left to right. So the left boundary is y equals root x. That's this guy. This boundary right here is where, well, this is the line where x is 9. So think of it from integrating a function on the left to a function on the right. So that gives us, the one on the right is just the constant 9. The one on the left, I need to solve this for what x is. On the right, x is 9. On the left, x is y squared. That's the key step here, is to take y as a function of x and invert it to get x as a function of y. Sorry. On the right, x is 9. On the left, x is y squared. I'm doing things in terms of y here. And y, the range of y values is from 0 up to 3. Okay, I'm going through this part kind of fast because, like I said, I just did this already. What's the only difference between what I'm writing here and what I did here is I just switched x and y. right? What I called x is here what I'm calling y. But it should give us the same area regardless. So as we already know, we're going to get 18 if we do that calculation. Who's new to this switching variables and doing it dy? Some people. Has anyone seen that before? Okay, cool. Good. Then it won't be totally new. I wasn't sure if that had been done before. But now let me give a harder example where it's a lot more important. This one wasn't all that bad. I'm going to use the same square root function. So this is x is y squared. And then I'm also going to use another parabola. Oh, I need this bigger, actually. So this is x equal to 2y squared minus 1. And this is x equals y squared. And the question is to find the area between the curves. So I just showed you this method where we switched variables to y. And I showed you that you can actually, you can apply that to a given problem, or you could apply x. So there's a choice. You have to make a choice as to which method you want to use. And the thing to take away from this is that in some problems, one method is way better than another. You can vastly simplify some problems by doing it dy instead of dx. This one was not such a problem. I'd say these two were about the same difficulty. They're both pretty fast. Maybe this one was actually easier, actually. But what if we forgot that we knew about switching to dy and tried to do this area? We run into a couple problems. For one, what's the function on top? Like, it kind of looks like it's this function, except over here, like this part's on top. In fact, like there's multiple function values here. So we have a serious problem in even saying what the function on top is for this region. There's a name for that. We would say that this is not vertically simple. So this region is not vertically simple. And what vertically simple means is if you draw a line, a vertical line through your region, it intersects it in only one segment. So the part where there would be an issue here is if I drew a vertical line right here. It actually intersects in a couple different segments. You can see I get a segment of intersection right here, but I get another one down here. So that's bad. That's why this region is not simple. Is this region vertically simple? Yeah, there's no part where we would get multiple different points of intersection. So this region, would this be vertically simple? Is there one function on top and one function on bottom at every point? Let's see, if we start drawing lines, okay, yeah, that's only one segment. Here, yeah, that's just one segment. Ooh. Here, that's just one. Here, that's just one. So this is on the other hand, this guy is not. Yeah, you can see right here, I get two different parts intersecting. So when it's not vertically simple, that means you have to be a bit more careful with setting up your area integral. And there's a couple things you could do, actually. There's choices here. Now, I was just showing you about changing variables. That's one way. There's actually another way, though, as well, which is to split this up into smaller regions. So we could split this, let's call this region 1. Let's call this region 2. And let's call this region 3. And I deliberately split that up in a way so that all three of those regions actually are vertically simple. So I can then just use the methods I've already described to get the areas of each of those three regions, add them up, and then I'll have my answer. You might notice you can probably save a little bit of time by noticing that 1 and 2 are the same in this example. Now, I was kind of debating whether to do this for this problem because, okay, here's what I wanted to show you guys was an example of choices and how one choice is clearly better than another. Because if you do it the way that I just described, it's a pain. It's a pain in the butt for this problem. So my plan was to go do that calculation, experience all the pain that went along with it, and then show you a much better way. I think I'm going to cut that short a little bit, but I'll just show you how to get started. So, for example, for what I labeled as region 1, let me just plot some points right here. This point of intersection right here, if I set y squared equal to 2y squared minus 1, I get y squared equals 1, which gives me y is equal to plus or minus 1. So this point is at 1. This point right here is at negative 1. And if you plug in 1 for y, you also get that x is 1. So for region 1, let's see. The function on, oh, I didn't even solve for what y is as a function of x, by the way. So from this, I would get y equals square root x as the function as this line. From here, I would get x plus 1 over 2 is y as a function of x. And then my expression for the area, it would be the integral, the expression for the area of region 1 is the integral from 0 to 1 of the function on top is, what's the one on top? The bigger, the x plus 1 over root 2 is on top in that region. And the one on bottom is just the root x one. Okay. I'm not going to actually finish this because, like I told you, it's kind of a pain. And then you also have to do it for the other two regions as well. So in the interests of time, I'm just going to say, take my word for it, this is really annoying. And now I'm going to show you the better way. So the better way is to switch it and do it dy instead of dx. Because, does anyone see why? There's actually a couple reasons why it's better. One is we don't got to split it up into like 3 different regions anymore. Because, yeah, it's only one region now. There's one function on the left and one function on the right. On the left is, that's the x equals 2y squared minus 1. On the right, that's x equals y squared. The y values start from -1 and go up until 1. So it'll be from y equals -1 up to 1, y squared minus 2y squared minus 1 dy. And this will give you the answer. Here, I'll just go do it real fast just to see what we get. What do we get? We get 1 minus y squared dy. So that's y minus y cubed over 3 from -1 to 1. That's going to give us a 2 minus 2/3, which is 4/3. And we're done. And trust me, this would have taken way longer if we did it in terms of x. It's quite a pain, actually, to do in terms of x. Let me write down the formula for integrals, for areas between curves, for integrals in terms of y. So this is for the case when you've got two curves. Let's say x equals g of y and x equals h of y. And if this is a point C and this is a point D, then the area between them is the integral from C to D of, okay, I say it's the one on the right minus the one on the left. g of y minus h of y dy. So that's basically the formula that I just used to get this area in this problem. Any questions on this? Yeah.
When we're integrating horizontally, it's right minus left, right?
Yeah. Anything else? Okay. I think I wanted to start on volume, but it's going to be kind of a lecture. So I'm going to just set you guys up with something and see if you can figure out what the best way to integrate it is. So here's one final example. How about let's find the area between y equals 6 minus x and x equals y squared. Yeah.
Will we test it specifically on this?
Well,
Like, do we have to know it, or if we're more comfortable with integrating using the x-axis, can we still do that?
you definitely should know how to do this. I mean, if this was a test, for example, and you did it the harder way but still got the right answer, if I didn't tell you which way you had to do it, then you would still get credit. But it wouldn't be that smart because there's a better way to do it. So yeah, you definitely should know how to do them either way. So if this was a homework problem, what would be the first thing you would want to do? Yeah, draw it. I love pictures, man. A lot of you guys are going to be engineers. Like having a physical grounding or intuition for these problems is crucial. So let's draw this. I've been doing this example all day. So that's this guy, or this curve. And y equals 6 minus x is a line like that. So the area between the two curves is this blue area. Then what? I gave you guys some options. We can do it in terms of x or in terms of y. Which is the better option? Yeah, how did you know that y is the better choice? Well, if we did it in terms of x, we would have to do like square roots. Well, for one thing, we would need, if we did it in terms of x, for one, we would need that y is the square root of x, and square roots are annoying. We'd also still have to split this into two regions, because there's one function on top here, and there's a different function on top here. So once again, this is a problem where you'll save a lot of time and trouble and hassle if you realize that the smarter way to do it is dx instead. How do we do that then? What's the next step? So say we've already decided to, let's do it dy. And I'm about to end out of time, so I think it's going to cut me off as soon as the podcast is going to cut off in 1 minute. Okay, let's finish this real fast. If 6 minus x is equal to